using equation number 1. It turns out there is another equivalent way to write covariance. What is that second way of writing this covariance? It turns out this is identically equal to this. Both the expressions 1 and 2 give you the same, evaluate to the same thing, which is namely the simpler form number 1. So I guess so this is I guess I need not, I mean this is more confusing than it needs to be, because this is mx and this is my. Okay, or maybe I'll write it one more time. Without erasing anything. So I am not saying that it's easier to see that this follows from this, so you can work from here upwards just by expanding this, and noting that as far as this outer expectation is concerned, the Ex is just a constant, right. So all we are doing is finding the expected value of x minus a into y minus b, right, but we are putting special values of a and b, right. We are putting a equal to Ex and b equal to Ey. Okay. So covariance xy is also a form of E of x, x1, x2 is what I wanted to point out, right. This is also this is a random zero mean random variable, so, right. So this is basically the same, and we will exploit this later also, right. It's so covariance xy is no different from E of xy in some sense, it's not directly E of xy, but it's E of x1 y1. So maybe we can think of it as write it like this, or x prime y prime, or whatever you want to call it, right. So this is the mean removed version of x, and this is the mean removed version of y. In this connection, I just want to point out that the quantity Exy itself, which yesterday we called the correlation of x and y, that terminology is used primarily in signal processing, right. If you go and look in statistics, you do not see the term correlation applied to this quantity here. Okay. So but since we are primarily doing all of this, or one of the applications that we are doing it is for signal processing, we will stick to the term, I mean there is no, why should we give up our usage of the term correlation for this, just because the statistics people do not call that the correlation, right. So what they call correlation I will mention later, but right, we are calling, so this is correlation in signal processing, right. Okay. So it turns out that this is a very important quantity. This, I mean the covariance of x and y is very important. We note that a couple of properties of covariance, right. Covariance of x comma y is the same as covariance of y comma x. It does not matter, it is very clear, the ordering makes no difference, right. And then what is the covariance of x comma x? What is this? The variance of x, right. So there is no right problem in taking the covariance of x with itself, you get back the variance of x, right. Okay. But in general covariance can be positive or negative, as we will see, or 0. In the case that covariance is 0, we call x and y as uncorrelated, right. That is probably why the statistics people did not like the term correlation to be given to this, because uncorrelated does not mean Exy is 0. But the term is stuck in signal processing, so we have to, since we will encounter, or you people when you study courses like adaptive signal processing and so on, you will run into more versions of Exy, which will be called correlation then also, so there is no reason not to call it correlation here, right. Okay. So now let us see how to use this correlation to do more interesting things, like the sum of multiple random variables like x1 plus x2 plus x3, for example. if I want to extend from 2 to 3, instead of going from x plus y, if I want to do this, so if I have 3 random variables and I want to find the mean and variance of x1 plus x2 plus x3, okay, what do I get? The mean of x1 plus x2 plus x3, as I said yesterday, is always the sum of the means, individual means. This is no big deal. We'll just write it again for make sure that this is never an issue for anybody here, right? What about if you want to find the variance of this, you first want to find this first. Now note that when there is already, right, you don't have to put an extra brackets around the square, when you can just write it like this, like that's what we wrote x plus y whole squared yesterday, right? We can dispense with these outer brackets. Here also I could have dispensed with the outer square brackets, right? This is basically this matching this. I could have thrown them away, but I am just keeping it here and here also just for clarity, that's all, right? Okay, but otherwise I think I have done a correct matching, right? I don't have an automatic editor here which highlights the matching bracket, but but otherwise, right? Okay, coming back to this, so we don't need to keep putting the outside square brackets, right? We can just simply write it like this. So it turns out if you expand this out like we did yesterday, you get all those, basically it will be written like this: sigma exi squared, I equal to 1 to 3 in this case, plus what? 2 double sigma e of xi xj. What limits do I have to say here? I just simply put I less than j, right? I should be less than j, let's say, and then 1 to no, not equal, the equals comes here, right? So the only I want I to be strictly less than j out here, x1 x2 x2 x3 and x1 x3, right? So it's just I less than j. So you can, and of course let's say I going from well, j going from 2 to 3, or I going from whatever, in this case 1 to j minus, in this case it is I going to 1 to j minus 1. So instead of worrying about the limits of I and j, we just simply write I less than j, right? So essentially you can think of it as a single sum over all possible I less than j. I think that's the simplest way of looking at it. Anyway, if you do the simplification, if you remove the mean squared, it turns out that you will get the variance of the sum. This is what we are after. What will this be equal to? So this will be the sum of the variance I equal to 1 to 3 in this case, or n 1 to n if you have n of them, plus what? Twice the again I will put I less than j here, right? Simple. Twice the covariance of sum of the covariance of xi xj for, and this 2 is very important, right? Comes from here. So you can see how the covariance, and in fact this is nothing but a covariance. So this is nothing but covariance of xi comma xi, and this is covariance of xi comma xj. So the covariance becomes very handy to deal with sums of random variables essentially, right? An application of this is to find the variance of the binomial distribution without doing any complicated summations. How is this directly applicable to finding the variance of the binomial distribution? Because binomial random variables are sums of Bernoulli random variables, IID Bernoulli random variables, that too, right? Let me write y instead of x, binomial n comma p, which implies that y is the sum of n Bernoulli, IID Bernoulli random variables, n 1 to n xi is Bernoulli p IID, isn't it? Always, right? Any binomial is the sum. So therefore what is E of y? It's just sigma E of xi. What is this? NP. So I can get the mean without, in one shot, without worrying about any manipulations of the PMF at all, isn't it? Likewise the variance. It turns out that since they are IID, what happens to these cross covariance terms when all these random variables are all of them pairwise independent or pairwise uncorrelated? Remember, IID or independent means they have to be pairwise uncorrelated, and covariance is always defined only for two at a time. You don't have the concept of like in independence you don't say x1, x2, x3 are uncorrelated. It means they are pairwise uncorrelated always. And if you have a collection of independent random variables, they must be pairwise uncorrelated, right? So since the xi are pairwise uncorrelated, what do you get? What does this mean? This means that covariance xi, xj is 0 due to independence, right? What do we get? What is E of y? Oh, sorry, what is sigma of, going back to this equation here, what is variance of y? Variance of y is what? Only this. Right? Only this term. This term will automatically go to 0. I equal to 1 to n variance of xi, which is, remember the variance of a Bernoulli random variable is p into 1 minus p minus p squared. So what do you get? You get the standard n times p 1 minus p, which is the variance of the binomial. You can put a tick against that. This is exactly what we got earlier by a long roundabout calculation of E of y and E of y squared and so on, which is not required because you just write y as a sum of x's. This is okay to everybody. Let me next take up, right, another just to point out that independence always implies uncorrelatedness, but uncorrelatedness does not imply independence. I mentioned that in yesterday's class. Right. So an example of, right, uncorrelated but not independent, but very highly dependent. Uncorrelated but highly dependent. There are several such examples you can, right, random variables, right. What is this example? So I have, let's say x is, there are many possible, I am just picking up one. I am picking up a pair that we have already studied. The spinning pointer pair, where we are looking at the x and y coordinates of the tip of the pointer after it comes to rest, right. Let us say this, the angle is the uniform 0 to 2 pi. We have already noted that x and y are highly dependent simply because x squared plus y squared is always equal to 1 with probability 1. Right. There is no way that in your wildest dreams that you can imagine x and y to be independent in this case, right. In fact, if you know x, you know y up to a sign, right. It can only be plus of something or minus of something. So clearly x and y are highly dependent in such a situation, but you can easily show that x and y are uncorrelated. In fact, x and y do not have a healthy distribution, joint distribution, because their joint, right, the omega xy is only the circle, not the inside of the circle, but only on the circle. So you cannot write a healthy f of fxy. I think we mentioned that also. But it turns out using Lotus you can easily evaluate the exy. So in general, how does this the Lotus principle work, right, when you have x equal to, for x equal to let us say h of u and y equal to, or let us say g of u and y equal to h of u, what, where u is some arbitrary random variable. If you define two other random variables x and y, in general x and y do not have it is a special case of this, they do not have a PDF, a joint PDF, right. You have to struggle to, you know, in the sense if you want to express the joint behavior, you have to go to some other notation to describe it, which we are not doing in this course, right. But exy, it turns out is just again almost unconsciously you write it as what? E of, even without worrying, you know, if we are giving it a second thought, what will you write exy as? E of gu into hu, which is some e of some other function of u. See how this Lotus principle works? I am not sure how well this is going to come, but I am going to write here, right. I am hoping that recording up to here is going to work, because I don't want to, I want to use a full board, right. So I mean what I am trying to say is that this is no different from any other e of some function of u. You can think of gu hu product as yet another function of u, and do not worry about the fact that gu is some x and hu is some other y. Okay. So this is what I want you to take home more than anything else, right. Even though x and y do not have a healthy PDF, they still have a healthy exy, which in this case is going to be what? For the above example, so this is just this example, it turns out that ex and ey will both be 0, and exy, you know, do this and tell me what exy is supposed to be. Exy, it turns out, is nothing but e of cos theta sin theta, and by simple trigonometry it is, what is cos theta times sin theta? It is sin 2 theta divided by 2. It is easier to write it like that. So it is half of e of sin 2 theta, and you can easily show this is also 0 just by simple integration. It is 2 cycles of a sine wave. What is the average of 2 full cycles of a sine wave? These were 1 cycle of a sine wave. This is 1 cycle of the cosine, this is 1 cycle of the sine, so both 0. This is 2 cycles of the of sin theta in 0 to 2 pi. So this is also 0 for the given PMF of theta or PDF of theta. So what can you say about x and y? You go back and apply this formula, what do you get? You get 0, no? This is 0, this is also 0. So hence in this case x and y are highly dependent but uncorrelated, or you should say uncorrelated but highly dependent also. But so this turns out this correlation is only, it tells you something, that is, if we will say, as we will see later, there are some limits to the correlation if you normalize it properly. It's more useful when it approaches those limits rather than if it is close to 0. If it is close to 0, it does not give you any information at all about x and y. But as we will see in just a little while from now, right, there are some values of the correlation which do tell you a lot about x and y. Okay, we will defer that. So is this okay? this example. Likewise, you can cook up many examples of x and y which are correlated, which are uncorrelated but heavily dependent. For example, you can take x to be x itself, y to be x squared, in which case E of xy is what? If x is x and y is x squared, what is E of x? It is, sorry, E of xy is E of x cubed. Okay, and any symmetrical PDF on x, for example u minus 1 1, will make E of x 0, it will also make E of x cubed 0. So E of x squared may not be 0, but does not matter. So in this equation, if I want this covariance to go to 0, it is enough if one of these go to 0 along with this. It is not necessary that both of these, all of these should go to 0. So x and x squared can be uncorrelated for a symmetric PDF of x. Okay, maybe, well, I do not have time to space here to keep writing all that, but please note it down. X and x squared are uncorrelated but highly dependent, obviously, when x has a symmetric PDF. For example, 0 mean Gaussian.